A cosmic butterfly glows with the light of a dying star. Planetary nebulae are the final, beautiful shrouds of sun-like stars, but their beauty is a mask for profound strangeness. By the end of this journey, you will know 25 discoveries that completely upend what we thought we knew about stellar death. Why do these glowing shells form into impossible shapes? And what mysterious forces launch bullets of gas at supersonic speeds? We are about to dive into the weirdest corners of these celestial phenomena. What do you believe is the most beautiful mystery in the cosmos? Our journey into the strange begins with a simple mistake. The very name Planetary Nebula is a cosmic accident, a label born from the limitations of 18th century telescopes. When the astronomer William Herschel first observed these faint, glowing patches through his eyepiece, they appeared as small, greenish disks. They looked to his eyes almost exactly like the distant planet Uranus, which he had famously discovered. He called them planetary nebulae, believing them to be some new class of celestial object related to worlds. For decades, this beautiful misnomer stuck, shaping how astronomers perceived these mysterious smudges of light. They were catalogued and studied as odd planetary curiosities, their true nature completely hidden. It was not until much later, with the advent of powerful modern telescopes and spectroscopy, that the stunning truth was revealed. These were not planets at all, but the final, breathless sighs of dying stars. That faint green glow was the signature of oxygen being energized by an invisible, blistering stellar core. The entire beautiful structure was a rapidly expanding shell of gas, a funeral shroud being blown into the void. So the first truly strange discovery about planetary nebulae was that we had named them completely wrong. It is a perfect reminder that our understanding of the cosmos is often framed by the tools we have at hand, and that sometimes the most fundamental truths are hiding in plain sight, waiting for a better lens to reveal them. This beautiful misnomer was only the beginning of the strangeness. When we finally saw planetary nebulae for what they truly were, we expected to find simple, elegant spheres. After all, a star is a sphere, and if it gently puffed away its outer layers, logic suggested the resulting cloud should be a perfect, expanding bubble. But the cosmos had a different, far more artistic vision. Instead of uniform spheres, our telescopes revealed a gallery of impossible forms. Delicate hourglass structures, known as bipolar nebulae, stretched into space like cosmic butterfly wings. Elegant elliptical rings glowed with ethereal light, some twisted into pinwheel spirals as if a giant hand had stirred the stellar gas. Others presented complex, cloverleaf shapes with multiple lobes, defying any simple explanation. This riot of forms was the second great discovery, and it delivered a shocking blow to early theories. The serene, spherical death of a star was a fantasy. Reality was messy, asymmetrical, and breathtakingly intricate. This posed a monumental question. If a dying star is essentially a sphere of superheated gas, what invisible sculptors are at work in its final moments? What cosmic forces could possibly twist a star's last breath into an hourglass, a ring, or a spiral? The answer lies hidden in the star's secret history and its death throes, pointing to unlikely artists like hidden companion stars, powerful magnetic fields, and violent jets screaming from the poles. The shape of a planetary nebula is not an accident. It is a fossil record of a hidden struggle, a signature written in light that we are only just beginning to decipher. The gallery of impossible shapes was just the first clue to a deeper violence. Within those beautiful forms, astronomers spotted something even more peculiar, tiny knots of rebellion racing against the flow. In many bipolar nebulae, especially those elegant hourglasses, they found pairs of small, compact blobs positioned like opposing sentinels along the central axis. These were not part of the gentle, expanding shell. They were something else entirely, and they moved with terrifying speed. We call them FLIERs, an acronym for fast low ionization emission regions. The name itself tells a story, fast because they rocket outward at supersonic speeds, often hundreds of kilometers per second, far outpacing the main nebula shell. Low ionization, meaning the gas within these blobs is cooler and denser, with its atoms missing fewer electrons than the intensely energized gas around them. They are like icy bullets fired into a superheated furnace. Their very existence is a profound puzzle. How does a dying star, in the process of calmly shedding its outer layers, suddenly decide to launch a pair of precise, high-velocity projectiles? What mechanism could possibly create such compact, dense knots and propel them on opposite escape trajectories with such incredible force? The leading theories sound like chapters from a stellar thriller. One suggests a final, violent convulsion known as a late helium shell flash, where the star's core reignites in a last spasm, blasting material out in focused jets. Another points the finger at an unseen companion star, a cosmic accomplice whose gravity could funnel and accelerate material into tight, high-speed beams. Yet the exact trigger remains elusive. These FLIERs are more than just strange features. They are ballistic mysteries, fossilized impulses from a star's final moments that we are still struggling to decode. Those supersonic bullets point directly to a hidden partner in the crime. The mystery of the impossible shapes finds one of its most compelling solutions not in a single dying star, but in a cosmic duo. Discovery number 4 reveals that many, perhaps even most, planetary nebulae are sculpted by the gravitational hand of a binary star system. The serene death of a lonely star is a rarity. Instead, a chaotic, intimate dance between two stellar bodies often dictates the final, beautiful form. Picture a typical sun-like star nearing its end. Now imagine it has a companion, a smaller star orbiting close by. As the dying star swells into a red giant, its outer layers become so tenuous that the gravity of its companion begins to steal material. This stolen gas doesn't just fall onto the smaller star, it spirals around it, forming a flat, spinning disk of superheated matter called an accretion disk. This disk becomes the universe's most powerful sculpting tool. It acts like a cosmic nozzle, funneling and collimating the dying star's outpouring gas into two incredibly focused, high-speed jets that scream out from the poles of the system. These jets punch through the expanding cloud of debris, inflating lobes and carving out the classic bipolar or hourglass shape we see so often. It is a stellar sandblaster on a galactic scale. But the influence doesn't stop there. The orbital motion of the two stars themselves adds another layer of complexity. As they whirl around each other, their combined gravitational field churns the ejected material, potentially creating spiral patterns or warping the nebula into those elegant, asymmetrical ellipses we observe. In some extreme cases, the companion might not even be a star at all. Astronomers now theorize that a massive planet, a Jupiter on steroids, could be the culprit. As the dying star engulfs it, the doomed planet's gravity could still stir the pot sufficiently to break spherical symmetry, creating a simpler but still distinct non-spherical shape. The evidence for this is mounting. We have now directly observed central binary stars inside the hearts of many iconic nebulae. Their orbital periods, sometimes mere hours, provide the precise, dynamic engine needed for such intricate construction. This discovery transforms our view entirely. A planetary nebula is no longer just a star's death shroud. It is a fossilized record of a gravitational relationship, a final, luminous signature of a partnership that lasted billions of years, now etched across light years of space. The breathtaking butterfly wings in the sky are, in truth, the imprint of a cosmic dance. But the gravitational dance of a binary partner is not the only invisible sculptor at work. A fifth discovery reveals a hidden force, one that was long dismissed as too weak to matter in the chaotic final act of a star's life. We now find evidence that strong magnetic fields may be the cosmic architects behind some of the most precise and structured features we see. For decades, astronomers believed that as a star expanded into a red giant, its magnetic field would become hopelessly diluted, stretched thin across its vast, bloated surface. Its influence was thought to be negligible, like trying to direct a hurricane with a child's magnet. Yet, observations of several planetary nebulae have delivered a stunning contradiction. Using specialized instruments that can detect the polarization of light, scientists have mapped ordered, large-scale magnetic fields threading through the lobes of certain nebulae. These are not random, messy fields. They show a surprising degree of organization, often aligned along the same axis as the nebula's jets or lobes. This detection changes everything. A strong, organized magnetic field can act as a cosmic funnel. As the star ejects its ionized gas, a soup of charged particles, these particles become trapped by the magnetic lines of force. The field channels the flow, guiding and collimating the material into tight, focused streams. Think of it like squeezing a handful of iron filings into neat lines using a simple bar magnet. This magnetic guidance could be the very mechanism that shapes and sharpens the supersonic jets that create FLIERs and inflate bipolar lobes. It offers an elegant explanation for why some jets are so straight and narrow over incredible distances. Furthermore, these fields could help solve the puzzle of multiple, aligned lobes seen in some complex nebulae. If the dying star's core retains a strong, stable magnetic field orientation, it could launch successive outbursts of material along the same magnetic highway, creating layered structures all pointing in the same direction. This suggests the star's internal dynamo, the same engine that generated sunspots and solar flares during its active life, does not simply shut off. It survives in some form into the star's final dramatic acts, leaving its ghostly imprint on the surrounding nebula. The implication is profound. The beautiful, intricate shapes we admire are not just the product of gravity and wind, but also the last, powerful signatures of a star's magnetic personality, etched in glowing gas across the void. While magnetic fields shape the grand architecture, another discovery listens to the faint, precise whispers of water in the stellar wind. In the cold, expanding envelopes of certain dying stars, astronomers stumbled upon a natural microwave laser. We call them water masers. The word maser stands for microwave amplification by stimulated emission of radiation. It is essentially a laser, but instead of producing a beam of visible light, it emits an intense, coherent signal at microwave wavelength. In space, these are not manufactured devices, but natural phenomena that occur when conditions are just right. The surprise came when we found them emanating from the outer, cooler layers of a specific type of aging star known as an oxygen-rich asymptotic giant branch star. These are the direct precursors to many planetary nebulae, stars that are actively puffing away their outer layers in a slow, dense wind. Here is the profound strangeness. We are talking about water vapor, a simple molecule we associate with life and Earth, existing in the envelope of a star whose core temperature is over 100 million degrees. But in these cool, expanding shells far from the stellar inferno, water molecules can form when they are bathed in the right kind of infrared light from the star below, and when the density of the gas is perfect, something extraordinary happens. The water molecules get excited and begin to emit microwave radiation in perfect unison. This creates an incredibly bright, narrow beam of radio waves, a cosmic lighthouse blinking with a purity that man-made transmitters struggle to match. This discovery is far more than a cosmic curiosity. These water masers serve as our most precise probes into the hidden birth pangs of a planetary nebula. Because the maser emission is so coherent and comes from specific water molecules in specific locations, we can use them to map the geometry and motion of the gas with stunning accuracy. We can measure exactly how fast the stellar wind is expanding, and see if it is spherical or already showing signs of asymmetry long before the nebula becomes visible. They reveal turbulent clumps and shells within the wind, hinting at the instabilities that will later define the nebula's form. Listening to these water mazes is like placing a stethoscope on the chest of a star in its final millennia, hearing the precise rhythm of its dying breaths and predicting the shape of the phantom it will leave behind. The water mazes whisper of motion, but the full truth is a sonic boom written across light years. Discovery number 7 shatters any illusion of a gentle, drifting cloud. We now know the gas within a planetary nebula is not merely expanding, it is exploding outward at supersonic speeds. Typical expansion velocities range between 20 and 50 kilometers per second. To grasp that scale, a projectile moving that fast could circle the entire Earth in just over 20 minutes. This is not a serene farewell, it is a stellar hurricane. But the real violence happens at the boundaries. A dying star does not eject its atmosphere in one smooth, steady breath. Instead, it often experiences distinct phases. First, a slow, dense wind of material puffs away over thousands of years. Then, near the very end, the exposed stellar core revs up to unimaginable temperatures and unleashes a torrent of far faster but much thinner ionized wind. This creates a cosmic demolition derby happening in slow motion. The later, faster wind catches up and violently slams into the earlier, slower ejected shell. The collision point is a shock front, a titanic wall of energy. Think of it like a supersonic jet plowing into a wall of fog, the moment of impact compressing and superheating the gas to millions of degrees. This is where the nebula's intricate anatomy is forged. The shock fronts are the sculptors of the bright, sharp rims we see defining many nebula lobes. They also generate the delicate, filamentary structures that lace through the interiors like wrinkles in a cosmic curtain frozen at the moment of impact. The energy released in these collisions is so immense it does something astonishing. It makes the nebula glow in X-rays. This was a later, confirming discovery, the detection of high-energy radiation from what was once thought to be a cool cloud of gas. It was the definitive proof of this violent internal mechanics. So the beautiful, ethereal glow of a planetary nebula is not a soft, uniform light. It is the fierce radiance of continuous, invisible car crashes, a luminous battlefield where one wind from a dying star wages war on its own past. The nebula is not a cloud, it is a constantly evolving shock zone, a fossilized explosion we are watching unfold over millennia. That fierce radiance of shock fronts leaves a signature far beyond visible light. The eighth strange discovery came from listening to the cosmos with a different kind of ear, one tuned to the highest energies. Space telescopes like Chandra, designed to see the X-ray sky, turned their gaze toward these beautiful glowing shells and found something startling. From the hot interiors of some planetary nebulae, they detected the unmistakable flicker of high-energy X-rays. This was completely unexpected. The optical light we see comes from relatively cool gas, excited but not scorching. X-rays, however, are the signature of matter heated to staggering temperatures of millions of degrees. It was like discovering a blast furnace hidden inside a delicate glass sculpture. So what could possibly generate such intense heat in what appears to be a cloud of expanding, cooling gas? The leading theory points directly to the violence of those colliding winds. Remember the exposed stellar core, now a white dwarf, blazing with surface temperatures over 100,000 degrees. This tiny, ferocious ember does more than just illuminate the nebula, it screams. It emits a super-fast wind of particles, a torrent moving at thousands of kilometers per second. This supersonic blast wave races outward and slams with unimaginable force into the slower, denser shell of gas ejected millennia earlier during the star's red giant phase. The moment of impact is catastrophic. The gas at that collision front is not just compressed, it is shock heated to temperatures hotter than the core of our sun. Atoms are stripped bare, electrons are torn away, and the resulting plasma glows fiercely in X-rays. This creates a hidden, seething bubble of million-degree gas inside the cooler optical nebula. It is a structure completely invisible to traditional telescopes, a secret heart of pure violence. This discovery fundamentally changed our model. A planetary nebula is not a simple, homogeneous cloud. It is a layered, energetic ecosystem with a cool, bright photogenic exterior and a hidden, blistering interior where the true power of the dying star's core is still asserting itself, shaping its legacy from the inside out. Hidden within those violent shock fronts are tiny worlds of their own. The ninth discovery takes us on a microscopic journey into the nebula's anatomy, where we find strange, dense islands of matter swimming against the stellar tide. In many planetary nebulae, most famously in the Helix Nebula, the expanding gas is not smooth. It is studded with thousands upon thousands of bizarre, tadpole-shaped blobs. Astronomers call them cometary knots, and they are one of the most hauntingly beautiful small-scale structures in the cosmos. Each knot is a colossal globule of relatively cold, dense molecular gas and dust. Picture a cosmic droplet with a bright, glowing head and a long, faint tail streaming behind it like a miniature comet. But these are not comets, and their scale is almost incomprehensible. A single cometary knot can be as wide as our entire solar system. Their most striking feature is their perfect alignment. Every single one of these tadpoles points its tail directly away from the central, dying star, as if caught in a fierce, radiant wind. And that is precisely the key to the mystery. The current theory suggests these knots are the remnants of the star's own outer atmosphere, the last clumps of its former self. As the star shed its outer layers, instabilities in the expanding shell may have caused the gas to fragment and condense into these dense, self-gravitating blobs. They are like lumps in a cosmic batter, refusing to mix smoothly, but then the environment turned lethally hostile. The central white dwarf, now exposed, began bombarding everything around it with a torrent of deadly ultraviolet radiation. This intense UV light acts like a cosmic blowtorch, striking the dense knots. The side facing the star gets superheated, causing the gas to boil off and stream away, forming the long, glowing tail. This process is called photoevaporation. The knot is literally being evaporated by starlight, sculpted into its cometary shape by its own destruction. Yet here lies the central puzzle. Given the ferocious radiation and the violent, supersonic winds raging through the nebula, how do these fragile, cloud-like structures survive at all? They should be ripped apart and vaporized in a cosmic instant. Their continued existence suggests they are far denser and more resilient than they appear, perhaps with strong internal magnetic fields or complex chemistry holding them together against the onslaught. Each cometary knot is therefore a miniature drama, a battle between condensation and evaporation, between the ghost of the star's past and the fury of its present. They are not just decorations, they are the last, tenacious fragments of a giant, clinging to existence in the furnace of its own making. The survival of those dense knots speaks to the nebula's complex chemistry, but the gas itself holds an even more direct message from the grave. Discovery 10 uncovers the strange chemical fingerprints found in these glowing shrouds, signatures written not in shape but in elemental light. When astronomers pass a nebula's glow through a spectroscope, they break its light into a rainbow barcode, and that barcode tells a story of cosmic alchemy. The composition is never just simple hydrogen and helium, the pristine ingredients of the young star. Instead, we find these nebulae are strangely enriched with heavier elements like carbon, nitrogen, and oxygen. This is the star's final confession, revealing the secret nuclear fusion that occurred deep in its heart and, crucially, in its final death throes. During its red giant phase, the star becomes a turbulent chemical factory. Convection currents, like giant boiling pots, can dredge up material from the interior where nuclear burning has transformed elements. This process, called dredge-up, brings the newly forged atoms to the stellar surface. Later, intense thermal pulses can mix the star's layers even more violently. When the star finally sheds its envelope, all this processed material is blasted into space. The result is that a planetary nebula becomes a unique chemical fossil, its composition a direct record of the star's internal history. Some nebulae show extreme anomalies, like being incredibly carbon-rich, their spectra dominated by the soot forged in helium-burning shells. Others might show unexpected overabundances of helium or nitrogen, clues to which fusion cycles dominated the star's final millennia. This means no two planetary nebulae have exactly the same chemical signature. Each is a custom blend, a one-of-a-kind elemental cocktail mixed in the furnace of a dying sun, and then poured out into the galaxy to eventually seed future generations of stars and planets. The beautiful glow is in essence the visible ghost of a star's hidden nuclear fires. That chemical fingerprint is not always the final word. In one of the most bizarre twists of stellar evolution, the dead can briefly return to life. Discovery 11 reveals the astonishing phenomenon of the born-again star. Picture a cosmic story that seems finished. A sun-like star has shed its layers, a beautiful planetary nebula expands into the void, and at its heart, the exposed core has cooled into a white dwarf, a fading ember. The funeral is over, but for a rare few, the story has a shocking second act. Deep within that white dwarf, a final reservoir of unburned helium can become unstable. When it does, it triggers a cataclysmic event known as a very late thermal pulse. In this stellar Lazarus act, nuclear fusion reignites with violent fury. The star, which had already died, is suddenly reborn. It swells back out at an incredible rate, ballooning from a tiny Earth-sized white dwarf back into a red giant in a matter of mere decades. This is not a slow, graceful process. It is a stellar explosion in reverse. The reborn giant then does something surreal. It expands so rapidly that it literally swallows its own planetary nebula. The beautiful, ancient shell of gas that marked its first death is engulfed by the resurrected star, consumed and hidden from view, but the rebirth is short-lived. The new fusion furnace is unstable. Soon, the star undergoes a second, violent death. It ejects a new shell of material, but this shell is chemically bizarre. Having burned through most of its remaining hydrogen in the brief, intense pulse, this new ejector is often hydrogen poor, rich instead in helium and the products of this late-stage burning like carbon. The result is a nebula within a nebula, a cosmic Russian doll. We have witnessed this happen. The most famous case is an object known as Sakurai's object. In the mid-1990s, this faint star in the constellation Sagittarius suddenly began to brighten dramatically. Within a few years, it transformed from a dim white dwarf into a cool giant. Spectroscopic observations confirmed it was engulfing a previously unseen shell of ancient material, the ghost of its first nebula. Today, we watch as it is ejecting a new, distinct shell, creating a complex layered structure that future astronomers will study for millennia. This born-again phase is a fleeting cosmic paradox, a reminder that even in the cold depths of space, finality can sometimes be rewritten. That brief, violent rebirth is an extreme example of chemical chaos, but even in a single death, the star's final elements are not always scattered evenly. Discovery 12 reveals a strange chemical map within some nebulae, where heavy elements like iron are not mixed smoothly into the glowing gas. Instead, they are concentrated in specific regions, perhaps one lobe of a bipolar structure or a particular arc within a ring. This is an asymmetric metal distribution, and it forces us to rethink the star's last moments. For decades, we assumed that the dredge-up process, which brings newly forged elements from the core to the surface, was a relatively uniform affair. The star, being a sphere, should mix its internal ingredients like a slowly stirred pot before pouring them out. But these clumpy chemical maps tell a different story. They suggest the final convulsions were lopsided at the most fundamental level. The mechanisms that brought iron or carbon to the surface may have been stronger on one side of the star than the other, perhaps due to a wildly asymmetric magnetic field or the gravitational tug of a companion star stirring the pot unevenly. Alternatively, the ejection event itself may have been profoundly non-uniform. Instead of a smooth, spherical shedding, the star might have literally belched material in great, chemical-rich plumes from specific hotspots on its surface, like a geyser erupting on a cosmic scale. This means the beautiful shapes we see are not just empty shells, they carry an internal chemical blueprint of the eruption that formed them. One glowing lobe might be rich in iron, while its opposite twin is iron poor but packed with carbon. The nebula becomes not just a sculpture of gas, but a three-dimensional painting where the colors, representing different elements, were applied from a splattering, chaotic palette. This chemical asymmetry adds a profound new dimension to the shaping mystery. It tells us the star did not die with a sigh, but with a fitful, uneven cough, leaving its elemental legacy scattered in strange, lumpy pockets across the light years. These uneven chemical splatters hint at a deeper mystery, one that goes to the very heart of what a nebula is made of. Discovery 13 presents us with a fundamental accounting error in the cosmos, the missing mass problem. When astronomers carefully weigh a planetary nebula, measuring the total amount of glowing, ionized gas, they consistently come up short. The brilliant, visible shell often contains only a tiny fraction, perhaps 10 to 20%, of the mass we know the parent star must have ejected during its death throes. It is a staggering deficit. If a star shed an entire solar mass worth of material, we can only see the equivalent of a large planet's worth glowing before us. So where is the rest? This is not a trivial oversight. It is a major unsolved puzzle that challenges our entire understanding of how these structures form and evolve. The leading theories point to material hiding in plain sight, informs our eyes and most telescopes cannot easily see. A large portion of the missing mass likely exists in a much cooler molecular state. This gas is not energized by the central star's ultraviolet fury, so it does not glow in the familiar optical light. It is a dark, cold shroud cloaking the brilliant inner nebula, detectable only through its faint radio emissions or by the shadows it casts against background starlight. Another possibility is that a significant amount was lost much earlier, in a slow, dense wind during the star's long red giant phase. This material could have drifted so far out that it is now incredibly faint and diffuse, forming a vast, invisible halo that our current instruments struggle to map. There is even a more dramatic suggestion that some of the mass was ejected in a direction we simply cannot observe, or was accelerated to such high speeds it escaped the nebula's vicinity entirely. This mass discrepancy forces a humbling realization. The gorgeous, luminous sculptures we photograph are merely the tip of the iceberg, the brightly lit inner chamber of a far larger and darker crypt. Our models of stellar evolution are based on predicting how much mass a star loses, and if we cannot find that mass in its final monument, it means a crucial piece of the death process remains hidden in the shadows. The missing mass was not truly gone, it was simply hiding in the dark. Discovery 14 illuminates this hidden realm through a different kind of light, the warm glow of the infrared. When astronomers pointed telescopes like the Spitzer Space Telescope and the James Webb Space Telescope at planetary nebulae, they saw beyond the brilliant optical shell. They detected the faint signature of vast reservoirs of molecular hydrogen. This is not the hot, ionized hydrogen that gives nebulae their classic red glow. This is H2, cold hydrogen gas where two atoms have bonded together into simple molecules, existing at temperatures just tens of degrees above absolute zero. This molecular hydrogen forms immense cold structures that often envelop the visible nebula like a frigid cocoon. In many cases, it arranges itself into perfect rings or complete shells that sit just outside the boundary of the hot, ionized region. The Ring Nebula, for instance, shows a stunning infrared halo of molecular gas that dwarfs its famous glowing ring. This is a profound revelation. It means a planetary nebula is not a single entity, but a multi-phase environment, a cosmic Russian doll with layers of vastly different states of matter. At the center, the searing white dwarf, surrounding it the hot, ionized plasma glowing in visible light, then a transition zone where atoms recombine. And finally, this vast, dark shroud of cold molecules, the true bulk of the star's ejected envelope. The presence of this molecular hydrogen solves a piece of the missing mass puzzle, but it creates new questions about chemistry. How does delicate molecular hydrogen survive the blistering ultraviolet radiation from the central star? The answer lies in shadows and shields. The dense knots and clumps we discussed earlier, along with dust grains, can provide enough protection. They act as umbrellas, blocking the destructive UV light and allowing pockets of gas to cool and molecules to form. Furthermore, the chemistry is self-reinforcing. As hydrogen molecules form on the surfaces of dust grains, they help cool the gas further, allowing more molecules to form in a cascading process. This cold molecular component is not a passive bystander, it is an active participant in the nebula's evolution. Its gravity can influence the expansion of the inner regions, and its structure holds clues to the geometry of the very first, slowest winds from the dying star. So the beautiful optical nebula is merely the inner heart of a much larger, darker, and chemically complex beast. A ghostly giant we are only now learning to see in the cold light of the infrared. This vast, dark molecular shroud forces us to look at the entire nebula as a single, complex system. But what if we zoom out even further? Discovery 15 presents a statistical mystery so strange it connects the death of a single star to the grand architecture of our entire galaxy. When astronomers studied the orientation of bipolar planetary nebulae in the dense central bulge of the Milky Way, they noticed something peculiar. The symmetry axes of these celestial hourglasses, the imaginary line running through their twin lobes, did not appear to be randomly pointed in all directions as one would expect. Instead, there seemed to be a curious statistical preference for these axes to align parallel to the plane of our galaxy. It was a subtle signal in the data, a whisper of order amidst cosmic chaos, but if real, its implications are staggering. Think of what this means. Each bipolar nebula is shaped by the spin axis of its progenitor star or binary system, the direction from which its jets erupted. This finding suggests that the spin axes of many dying stars in the galactic bulge are not randomly oriented. They are somehow influenced, perhaps from the very moment of their birth, by the overall rotation and angular momentum of the Milky Way itself. It is as if the galaxy's slow, majestic spin leaves a faint imprint on the way its constituent stars live and die. One leading theory points to star formation. Stars are born from collapsing clouds of gas and dust, and these clouds are themselves shaped by the galaxy's magnetic fields and rotational forces. If the natal cloud has a preferred orientation, the stars that form within it might inherit a similar spin alignment, like seeds scattered by a wind, all landing pointing in roughly the same direction. This primordial alignment could then be preserved over the star's multi-billion-year life, only revealing itself in the geometry of its final death throes. However, this idea is hotly debated. Skeptics argue it could be a selection effect, a trick of perspective and observation. Perhaps bipolar nebulae aligned in a certain way are simply easier for us to identify and categorize from our particular vantage point within the galaxy, creating an illusion of alignment in the data. Untangling this statistical knot is incredibly difficult, requiring precise three-dimensional mapping of hundreds of nebulae, yet the possibility remains tantalizing. It hints at a profound and mysterious connection, a thread linking the intimate death of a sun to the cosmic whirlpool of 100 billion stars. The shape of a stellar ghost might carry not just the memory of its own life, but a faint echo of the galaxy's immense spin. The subtle alignment of galactic ghosts is a whisper from the past, but some nebulae offer a far more direct way to rewind time. Discovery 16 involves a cosmic illusion so perfect it defies intuition, the phenomenon of light echoes. We are accustomed to seeing events unfold at the speed of light, but in the dusty halls of certain planetary nebulae, we can watch an event replay itself over decades, creating the ghostly impression of motion faster than light itself. The stage for this illusion is set by a sudden, violent flash from the central star. In its final death throes, when the hot stellar core is first exposed, it unleashes a blistering pulse of ultraviolet radiation, a flashbulb of cosmic proportions that ionizes the surrounding gas in an instant. This flash, however, does not just illuminate the nearby gas. It races outward in all directions at, of course, the speed of light. Now, imagine that years or even centuries before this flash, the dying star had already ejected shells of dusty material. These dust clouds sit at various distances like concentric spherical curtains hanging in space. When the flash of light finally reaches one of these distant dust shells, it scatters off the tiny particles, sending some of that light toward Earth. Here is where the magic happens. We see the nebula's main structure light up immediately from the flash ionizing the nearby gas. But years later, we then see a new outer ring of light suddenly appear, as the echo of that same flash finally reaches a more distant dust shell and scatters toward us. As time passes, this echo appears to expand outward from the central star at a tremendous, impossible rate. The Hubble Space Telescope captured this perfectly in the Egg Nebula. Over several years, it watched a faint, ghostly halo appear and seemed to expand outward. The apparent speed of this expansion, if interpreted as real physical motion, would be many times faster than light. But it is not motion at all. It is a trick of geometry and delayed light, a cosmic afterimage. This gives astronomers an extraordinary power. By studying the precise timing and structure of these light echoes, we can effectively look backward in time. Each echo is a fossilized snapshot of the star's intense flash, captured by a dust cloud at a specific moment in the past. By mapping multiple echoes, we can reconstruct the three-dimensional structure of the dusty environment and even study the properties of the original outburst itself long after the event is over. It is as if the nebula itself is an echo chamber, preserving the dying star's final shout for centuries, allowing us to listen to its reverberations one delayed whisper at a time. Light echoes are a ghostly replay, but the power of that central flash can illuminate far more than its own past. Discovery 17 takes us beyond a single nebula and connects the physics of a dying star to the fate of an entire galaxy. We have seen how a hot white dwarf bathes its ejected shell in ultraviolet radiation, causing the gas to glow. Now, imagine that same process but scaled up to a truly monstrous level. In the distant universe, astronomers have found a rare class of galaxies with a bizarre nickname, green bean galaxies. They are not green beans, of course, but enormous, faint galaxies that emit a strange, uniform greenish glow across their entire structure. The source of this glow is the same process that lights a planetary nebula, photoionization, but the engine is different. Instead of a single white dwarf, a green bean galaxy is powered by a central active galactic nucleus, a supermassive black hole that was recently and fiercely active. This black hole unleashed a tremendous flash of radiation, so powerful it photoionized a vast reservoir of cold gas stretching across tens of thousands of light years within the galaxy. The entire galactic cloud glows with a specific green hue of excited oxygen, just like the green tinge William Herschel saw in his first planetary nebulae. And then the central engine shut off. The active nucleus went quiet, but the light from that flash is still traveling outward. We are now seeing the aftermath, a brief cosmic moment where a galaxy-scale cloud of gas is glowing because it was illuminated by a flash that has already ceased, just as a planetary nebula glows long after the star's final pulse. This makes a green bean galaxy a planetary nebula writ large across an entire galaxy. It is the same physics of delayed fluorescence, the same process of a central engine lighting up a surrounding fog, but magnified by a factor of billions. This connection is more than a neat analogy, it is a fundamental validation. The principles we decipher by studying the delicate glow of a nearby stellar corpse apply perfectly to the most energetic and vast structures in the cosmos. It means the universe speaks a common language of light and matter, from the final breath of a sun to the death cry of a galactic core. The cosmic light show of a dying star is not just a spectacle of gas, it is a foundry for solid matter. Within those turbulent, expanding shells, chemistry works on a staggering scale to forge microscopic worlds. As the ejected gas expands and cools, atoms begin to stick together, first forming simple molecules, then clustering into motes of dust. But this is no ordinary soot. Spectral analysis reveals the presence of complex crystalline structures, including silicates, the same minerals that make up sand and rock on Earth. More astonishingly, some nebulae show the infrared fingerprints of even more exotic materials like tiny diamonds. These nanodiamonds are carbon crystals only a few billionths of a meter across, created in the high-pressure, chaotic environment of the stellar wind. Each one is a perfect miniature lattice, a cosmic gem forged in a furnace of fading starlight. This dust does not simply linger, it is blasted outward into the interstellar medium, where it will eventually become part of the raw materials for new solar systems. The most direct proof of this incredible journey comes not from telescopes, but from rocks that fall from our own sky. Inside certain primitive meteorites, scientists have found minute grains of dust that predate the formation of our solar system. These are pre-solar grains, literally stardust. By analyzing their isotopic signatures, their unique atomic fingerprints, we can trace some of these grains back to their specific stellar nurseries, including planetary nebulae. This means we can hold in our hands, with the aid of a powerful microscope, tangible pieces of ancient, dead stars. A speck of diamond or silicon carbide from a meteorite may have formed in the cooling envelope of a sun-like star that died over 4.5 billion years ago, long before our own sun ignited. This discovery ties the grand cycle of stellar life and death directly to our most local reality. The carbon in our bodies, the silicon in our rocks, the very dust from which Earth coalesced, was once processed and scattered by stars like these. A planetary nebula, therefore, is more than a tombstone. It is a prolific seed disperser, scattering the heavy elements and complex dust grains that will one day become the bedrock of new worlds and perhaps the chemistry for new life. That stardust carries the memory of a star's final chemistry, but the engine that illuminates it all is far from a steady beacon. The 19th discovery reveals that the central stars of planetary nebulae are often unstable, flickering actors on a cosmic stage. These tiny, searing white dwarfs are not always the quiet, cooling embers we might expect. A significant number are variable stars, their brightness pulsing or changing in irregular, dramatic ways. This is not a gentle flicker. Some undergo rapid pulsations, swelling and shrinking in size with periods of just a few minutes, causing their luminosity and temperature to swing wildly. Others exhibit more erratic changes, perhaps due to instabilities in their thin remaining atmospheres or from the gravitational influence of a companion star in a tight, chaotic orbit. This stellar variability has a profound and direct impact on the nebula itself. Think of the central star as a powerful ultraviolet lamp. When it brightens during a pulse, it floods the surrounding gas with more intense ionizing radiation. This causes the boundary between the hot, ionized gas and the cool, neutral gas, called the ionization front, to suddenly expand outward. When the star dims, the front contracts. The nebula is not a static sculpture, but a dynamic screen responding in real time to its flickering projector. Over years or decades, this can create observable changes in the nebula's illumination patterns. Brighter regions may fade as others suddenly glow more intensely, like a cosmic light show playing out in extreme slow motion. In some cases, if the star undergoes a particularly violent fluctuation, it could even trigger new shock waves or alter the chemical reactions within the gas. This variability forces us to see planetary nebulae as living, breathing entities, still intimately connected to and controlled by the erratic heartbeat of their tiny, ferocious cores. The beautiful glow we see is not a permanent monument, but a transient reflection of a star's last, unsteady breaths. The erratic heartbeat of a central star can become a full-blown stellar scream. For a truly extreme example, we must turn our gaze to a specific cosmic masterpiece, the Butterfly Nebula, known to astronomers as NGC 6302. This is not a gentle insect, but a titanic, raging structure that represents the most violent and energetic end of the planetary nebula spectrum. Its wingspan stretches over 3 light years, a distance so vast it would take a beam of light, the fastest thing in the universe, 3 full years to travel from one wingtip to the other. Within that immense form, the physics is pushed to terrifying limits. The nebula's bipolar lobes are not smooth and graceful. They are turbulent, riddled with complex knots and streamers that tell a story of multiple, catastrophic ejections. For decades, the central engine of this fury remained a mystery, completely hidden from optical telescopes by an incredibly dense, dusty waistband that girdles the star like a thick belt. It was only when we looked with ultraviolet eyes that we pierced the veil. What we found was staggering. The central star is one of the hottest objects ever detected in our galaxy, with a surface temperature screaming at over 250,000 degrees Celsius. That is over 40 times hotter than the surface of our own sun. This tiny, invisible inferno is the power source for the entire dazzling display, its intense radiation and ferocious winds violently shaping the expanding gas. The butterfly's history is one of sheer stellar violence. Astronomers believe the dying star did not shed its envelope calmly. Instead, it likely experienced a series of enormous, asymmetric outbursts, blasting material out in opposing jets at speeds exceeding 600,000 miles per hour. The dense dust at its waist may be the fallout from these convulsions, material so rich in heavy elements that it condensed into solid particles even in the searing environment. This nebula is more than a beautiful shape. It is a fossilized stellar death scream of epic proportions, a testament to the chaotic and furious energy that can be unleashed when a star dies not with a whimper, but with a cataclysmic roar. The cosmic violence of the Butterfly Nebula finds a strange, geometric counterpart in a quieter but no less mysterious corner of the sky. Known as the Red Rectangle, this nebula is one of the most perfectly structured oddities ever discovered. Its name comes from its appearance in early images, a deep crimson, almost rectangular frame of glowing gas. But higher resolution views reveal the truth is even stranger. The rectangle is not solid. It is an intricate X-shaped structure like 2 hollow cones placed tip to tip, with sharp rungs of glowing material connecting them like the rungs of a ladder. This creates a stunning geometric lattice, a piece of cosmic stained glass hanging in the void. Its intense red color is not from common hydrogen, but from a phenomenon called extended red emission, a mysterious glow linked to unusual forms of carbon-rich dust and complex organic molecules fluorescing under starlight. At the heart of this geometric marvel sits a confirmed binary star system, designated HD 44179. This pair, a hot star and a cooler companion, is locked in a tight orbit. The prevailing theory for the red rectangle's impossible shape involves a dense, dusty donut or torus that encircles this binary pair. Imagine a thick belt of dust and soot girdling the 2 stars. As they shed material, this outflow cannot escape evenly in all directions. Instead, it is funneled by the torus, forced to exit above and below the dense ring, forming 2 opposing cones of gas. Our view from Earth looks directly down the barrel of one of these cones, and we see the walls of both cones projected as an X. The sharp rungs may be periodic ejections from the stars, like puffs of smoke from a chimney caught in the stellar wind, creating a series of expanding rings that appear as rungs from our perspective. This nebula is a masterpiece of cosmic geometry, a testament to how precise physical conditions can sculpt chaos into near-perfect symmetry. Yet, the exact chemistry of its red glow and the detailed mechanics of its formation remain active puzzles, a beautiful proof that even in death, stars can leave behind puzzles of breathtaking precision. The geometric perfection of the red rectangle emerges from a delicate binary dance, but some stellar deaths are born from a far more violent merger. Discovery 22 pushes the very definition of a planetary nebula to its explosive limit. We must now consider a scenario where the central engine is not one dying star, or even a pair of orbiting stars, but the cataclysmic collision of two stellar corpses. This is the theoretically predicted, and likely very rare, formation of a planetary nebula from the merger of two white dwarfs. Picture the end result of a long gravitational tango. Two white dwarfs, the dense Earth-sized cores of long dead stars, spiral closer and closer over eons. Their final embrace is not gentle. If their combined mass crosses a critical threshold, it can trigger a runaway thermonuclear reaction, a titanic explosion. But in some cases, if the total mass is just below that detonation point, they may merge without a full supernova. Instead, the violent union creates a single, rejuvenated star, shrouded in a rapidly expanding cloud of debris blasted away during the merger. This cloud would be illuminated by the hot remnant, appearing for all the world like a planetary nebula, but its nature would be profoundly different. The chemistry of such a nebula would be a chaotic fingerprint of the merger. The gas would be enriched with the nuclear ash from the interiors of both white dwarfs, likely showing bizarre and extreme abundances of elements like carbon, oxygen, and neon, mixed in ways a single dying star could never produce. Its kinematics, its motion, would also tell a story of violence. The expansion would be far more energetic and likely less symmetrical than in a typical planetary nebula, with complex velocity patterns hinting at the brutal dynamics of the collision. Astronomers are actively hunting for these hybrid objects, and candidates like Able 41 are in their sights. In Able 41, the central source is a spectroscopic binary, a pair of stars so close they cannot be resolved, orbiting each other in a matter of hours. The nebula itself shows chemical peculiarities and a shape that suggests a turbulent origin. Objects like this blur the line between a peaceful stellar shedding and a violent stellar transient, reminding us that the cosmos has more than one way to sculpt a glowing shroud from the remains of dead suns. These violent mergers rewrite the rules, but the cosmos also records its history with a patient, rhythmic hand. A strange and beautiful pattern adorns certain nebulae, a series of perfectly concentric rings or faint arcs that encircle the central star like the ripples from a stone dropped into a cosmic pond. The most famous example is the Cat's Eye Nebula, whose intricate inner structure is surrounded by these ghostly, evenly spaced halos, earning it the nickname the Eye of Sauron. For years, these rings baffled astronomers. They looked like spiral density waves, the kind that shape galaxies, but the physics did not fit. These were not spiral arms, they were frozen, expanding shells. The answer lies in the star's final millennia, in a slow, rhythmic pulse that became its death knell. In the centuries before its grand finale, a dying sun-like star does not lose mass at a steady rate. Instead, it experiences periodic convulsions, intense thermal pulses in its helium-burning shell that occur roughly every few hundred to 1,000 years. Each pulse acts like a deep, seismic shudder, violently shaking the star's outer layers and triggering a brief but dramatic episode of enhanced mass loss. The star essentially coughs out a dense, spherical shell of gas and dust. Then it settles back into a quieter phase of slower wind, A few centuries later, another pulse coughs out another shell. This process repeats, creating a series of concentric ejections, each one expanding outward into the void. By the time the star's core is finally exposed and lights up the whole system, these ancient, dusty shells are illuminated from within. We see them not as continuous spheres, but as bright rings, because we are looking at the thin, dense edges of each expanding bubble, much like seeing the rim of a soap bubble. These rings are therefore a fossil record, a stellar seismograph. The spacing between each ring corresponds directly to the time between those final, pre-death pulses. They allow us to count backward and reconstruct the star's erratic heartbeat in its last few thousand years of life. The cat's eyes haunting halos are not a sign of destruction, but a meticulous chronicle, a series of time-stamped sighs that preceded the star's final, breathless collapse. Those concentric rings are the star's private history, but the final chapter is written by the galaxy itself. Discovery 24 reveals a fundamental truth: planetary nebulae do not die in isolation. They expand into a space that is not empty, but filled with the thin, diffuse gas and dust of the interstellar medium. This gentle galactic breeze becomes a formidable force over millennia, sculpting the nebula's final act. As the glowing shell races outward at tens of kilometers per second, it eventually begins to plow into this surrounding material. The effect is like a speeding boat hitting calm water. It creates a bow wave. Astronomers call this a bow shock, a compressed, often brighter rim of material where the nebula's forward expansion slams into the interstellar medium and is dramatically slowed. This interaction can warp the nebula's shape, creating a distinct flattening or asymmetry on the side facing its direction of motion through the galaxy. In some spectacular cases, we see a classic cometary shape with a bright, rounded head and a long, faint tail of material being stripped away and left behind. This is a breakout morphology where the nebula is literally breaking out of its own bubble and interacting with the wider galaxy. The consequences are profound. This collision does more than just change the shape, it mixes elements. The pristine, chemically enriched gas forged in the star's core now churns together with the ancient, primordial material of the interstellar medium. Heavy elements like carbon, nitrogen, and oxygen are injected directly into the galactic ecosystem, seeding future generations of stars and planets with the building blocks for rocky worlds and potentially life. The nebula's beautiful, often symmetric form is therefore a temporary youth. In its old age, its shape becomes a record of its journey through the galaxy, a flag rippling in the interstellar wind. Its boundary is no longer defined solely by the star's death throes, but by a negotiation between the force of its explosion and the gentle, persistent pressure of the galactic environment. The stellar ghost does not fade quietly, it leaves a lasting impression on the very fabric of space around it. That gentle pressure from the galaxy is the beginning of the end. Our 25th and final discovery looks beyond the beautiful glow, beyond the shock fronts and the intricate shapes, to the ultimate fate awaiting every planetary nebula. It is a destiny not of fire, but of quiet, inevitable dissipation. Over the next 10,000 years, then 50,000, then 100,000, the nebula will continue its relentless expansion. But as it grows, it thins. The fierce ultraviolet radiation from the central white dwarf, which gives the gas its brilliant glow, will slowly fade as the star itself cools into a black, silent cinder. Without that energizing source, the ionization front will retreat. One by one, atoms will recapture their electrons, and the spectacular emission of light will cease. The nebula will transition from a radiant sculpture to a cold, dark cloud of neutral gas and dust, drifting silently through the galactic void. Eventually, its expansion velocity will slow to match the random motions of the interstellar medium, and it will simply blend in. Its distinctive structure will be erased, its atoms scattered and mixed with the primordial hydrogen and helium of the galaxy. This is the strange, beautiful truth of the cycle. The iron in your blood, the calcium in your bones, the oxygen you breathe, these heavy elements were forged in the nuclear furnaces of ancient stars. A planetary nebula is the crucial delivery vehicle. It is the moment those newly minted atoms, created in stellar cores and dredged to the surface in a star's death throes, are gently released into the galactic ecosystem. They do not simply vanish, they become part of a vast cosmic reservoir. Millions of years later, a shockwave from a distant supernova or the simple gravitational pull of a passing spiral arm will compress that enriched cloud. Within it, a new generation of stars will ignite, surrounded by disks of dust and gas from which planets will coalesce. On those planets, chemistry will work with this inherited stardust to build mountains, oceans, and perhaps, in at least one remarkable case, the complex molecules of life. So when you look at an image of a glowing planetary nebula, you are not just looking at a tombstone. You are witnessing a stellar nursery in reverse, a moment of profound generosity. It is the death of one sun, yes, but also the scattering of seeds for countless futures. The butterfly's wings, the cat's eye, the delicate rings, they are all temporary, luminous signatures in a story of recycling that spans billions of years. They remind us that we, and everything we know, are literally made from the ashes of stars that died in beautiful, mysterious ways, their final breath becoming our first ingredient. We have traveled from a simple naming era to the violent frontiers of stellar death. Each of these 25 discoveries peels back a layer of the cosmic onion, revealing that a planetary nebula is anything but a serene final curtain. It is a misleading name, a gallery of impossible shapes sculpted by hidden partners and magnetic ghosts. It is a supersonic shock zone where winds collide and million-degree gas glows in X-rays. It is a chemical fossil, a periodic pulse recorder, and a prolific dust factory seeding the galaxy with the ingredients for new worlds. We have seen them aligned with the galaxy's spin, heard the whispers of water mazes, and watched light echoes replay a star's final flash. These are not static tombstones, they are dynamic physics laboratories, each one a unique experiment in hydrodynamics, magnetism, nuclear chemistry, and radiation playing out on a light-year scale. And in that grand, beautiful cycle lies our own profound connection. The iron in your blood, the calcium in your bones, the oxygen in your lungs, every atom in you heavier than hydrogen and helium was forged in a star and likely scattered into the void by an event just like this. You are literally made from the recycled remains of ancient stellar deaths, of cosmic butterflies that lived and died billions of years ago. So the next time you see an image of these glowing shrouds, remember you are not just looking at a distant mystery. You are looking at a chapter of your own cosmic ancestry. Which of these 25 strange discoveries left you the most awestruck? Share your thoughts in the comments below, and if you want to journey deeper into the universe's greatest mysteries, be sure to subscribe.